Gentlemen, from the Department of Electrical and Electronic Engineering and the City and Guilds College Association, a very warm welcome to the 11th Peter Lindsay Memorial Lecture. Peter Lindsay made a very generous benefaction to support students in need, but also to provide for an annual lecture in his name. And this is the 11th such lecture. Peter was a very highly respected scientist and a fascinating character. You can get some feeling for his pre-academic activities, that might be a good word for it, his very harrowing escape from Europe, by reading about it in the brochure which you've been handed. Our speaker this evening is Professor Neil Turok, who holds the Niels Bohr Chair at the Perimeter Institute in Canada. He's well known not only for his seminal contributions to our understanding of cosmology, but also as his founding of the African Institute for Mathematical Sciences, which operates in a wide range of countries, Senegal, Ghana, Cameroon, etc., as well as in Neil's native South Africa. Now, I could tell you more about Neil's many achievements, but you have come here to listen to him and not to me. So I would simply refer you to this same brochure where you can read about Neil's biography. And lose no time in inviting him to present the 11th Peter Lindsay Memorial Lecture.
Thank you. Thank you, Bob. It's a great pleasure to be back at Imperial. I was here 3 times as a PhD student, and then as a 5-year fellow, and then finally I returned to be a professor in physics department. And the second time I was here, I spent some time in this building, and I want to tell you the story, which I've just told Bob. So I came over here because there was a big computer which was just being burned in. And I wanted to do some very large simulations, and there was free time. We couldn't afford it in physics. So I came here and started it all going and put my student onto it, and then I went away for 2 months. And I just told him to run the same code with a different seed, for as long as I was away. And so, unfortunately, unbeknownst to me, 2 weeks after I left, a note was sent out to everyone to say that this computer is no longer free. So I arrived back to the head of the physics department, Tom Kibble, who was an extraordinary person and physicist. And he just received a bill for more than £10,000. And at the time, the theory group had a big budget cut. Even paper and pencils were in short supply. And but in his typical way, he said to me, the good thing about this bill is that it's so large that we'll never have to pay it. So that made me feel a little bit better. But fortunately, I wasn't fired. And I'm still here to tell the tale. So what I'm going to talk to you about today, I should tell you a little bit about Peter Lindsay and my connection with him, which I only discovered today, which is that my grandfather and grandmother were also refugees, and they left Eastern Europe because of the Depression in the 20s, and they escaped to South Africa. And Peter's, of course, real name is not Peter Lindsay. His original name is, which I've lost. Okay, is a, I guess, Ukrainian name. I can't see it now. But, you know, refugees are unusual people. My family had to be refugees twice, first from Eastern Europe to South Africa. And then in South Africa, my parents both made the mistake of becoming political activists. And for their troubles, they were put into jail. And then we finally left as refugees to the UK. And so I very much empathize with Peter Lindsay. I also note that he taught a course or actually wrote a textbook on quantum physics. And that's the topic of today's lecture, so another connection. Now, let's see if, yes, I'm a theorist. I call all of you real people, and I'm an imaginary person. Okay, so in the sense of complex numbers, real people are engineers above all, experimental physicists, people who actually discover how nature works. And then there are a bunch of annoying people who try to provoke all these real people into doing things. And that's my role. And so I'm going to tell you about how I believe the universe is actually quantum, and I also believe we're on the threshold of finding out what that really means and how that makes sense. But as you can see, I'm hopeless with making this work. Before I begin, I just want to pay homage to this gentleman here. I was very, very fortunate to work with Stephen in Cambridge, and we wrote a few papers together and spent many a pleasant afternoon together. He actually was one of the first patrons of the African Institute for Mathematical Science, and the only time he went to Africa was to visit our institute in Cape Town. I was very fortunate to introduce Stephen to Nelson Mandela. I have to say, it actually wasn't really a great meeting of the minds. You can kind of see from the way Nelson is sitting. Unfortunately, Nelson was probably rather similar with computers to me. Nelson, when he was in jail, obviously was kept away from computers, and he came out of jail, and computers were utterly foreign to him. And here was somebody actually speaking out of a computer. It clearly took him aback. He didn't quite know what to make of it. But Nelson very sweetly remembered my parents, and as soon as he heard my name, and was quite an extraordinary character. Now, the two of them shared a couple of characteristics. Both of them loved tea. Okay. Stephen would happily spend hours drinking tea with you, discussing in a very, very convivial way. In fact, his office was located off the tea room in Silver Street. And so invariably, he would sort of be present at this gigantic tea every afternoon. Nelson also liked tea very much. As any of you who've seen the film Invictus, which a great film, shows Nelson enjoying English tea. He says it's the one thing the English invented, which is a good thing. But the other thing they both shared was an extraordinary sense of humor. They were both brilliant at cracking the right joke at the right time. Very, very witty and able to put everyone at their ease. So in a way, I introduced them too late, but they really were rather similar. This was another meeting of Stephen with somebody like him. This is a shot of Stephen at Perimeter Institute, where I work, and we make a big deal out of public engagement and public outreach and bringing the community in. And so this little boy was playing in the park outside our institute, and I was going for a walk with Stephen in the park, and the little boy was in the playground, and he points at Stephen and says to his mum, "That's Stephen Hawking." And his mum said, "No way." And so nothing happened. We heard the yell, actually, but nothing happened. And then the next day, I got an email from the little boy's father saying, was that actually Stephen Hawking in the park? Because the little boy had read 5 of his books by then. And so then the boy came in to have the books autographed. Stephen very graciously agreed. But what I love about this photo is you see they're wearing the same shirt. And that's the other side of Stephen. He really was a little boy, very full of life and fun and curiosity. So this lecture is really in his honor. There will be a service at Westminster next Friday week. And I hope that'll be a time for us all to remember this incredible individual. So what I'm going to talk about is the quantum universe, and Stephen really was the pioneer in seriously trying to connect quantum mechanics to gravity, to black holes, to the universe itself. And he was absolutely path-breaking in this. He did very serious, very beautiful mathematical calculations. As I'll explain in the talk, they weren't always right. But, you know, true visionaries seldom are always right. Einstein himself made several mistakes. But because they're brave and they're not afraid of making mistakes, they open the way for others. So I explained halfway through the talk why I believe Stephen's proposal for the beginning of the universe was wrong, mathematically wrong. But at the end of the talk, I'll explain how it returns in an even simpler way. It turns out, I believe, the reason he was wrong is he wasn't bold enough. He went along with fashion to too great an extent. And I think his ideas will outlive the fashion that he went along with. So there are a few papers here. If any of you want to read about this, this is all work in progress. By the way, in theoretical physics, we just refer to papers by these telephone numbers. And if you type them into the internet, they will pull up the right paper. We always publish things online long before they actually appear in print. And all papers in our field are publicly available from the moment they are submitted to the archive. So that's a wonderful resource for everyone. So let me start. Now, there are not going to be many equations in this talk, so I better get one of them out of the way. Okay? You don't need to understand this equation at all, but it's a very neat summary of everything we know about physics. And to a large extent, this summarizes all of 20th century physics, this formula. So here we have Einstein's theory of gravity. Newton only survives as a constant in this formula. Then there's Maxwell's theory of electromagnetism, which was the basic, actually the basis for all of this, but it was also the model on which the theory of the strong nuclear force and the weak nuclear force were built. They're essentially copies of Maxwell's theory with a few small tweaks. And then there was Dirac's theory of the elementary particles, the theory of the masses of those particles coming from the Higgs field, which is H, and then this last H being the Higgs field, discovered recently. And my French colleagues always complained to me that there was no French person here, so I put a French person there. Okay. So, and he well deserves to be there. Lagrange, of course, invented the formulae of Lagrangians, and in the potential energy, which appears in the Lagrangian, first of all, fixes the Higgs field to its value, and second of all, more deeply, it actually tells you what the energy in the vacuum is. And so Lagrange certainly deserves to be there. Now, there's only one, so here, of course, we have the wave function. This is the amplitude for any physical process. The square of it gives the probability. And essentially, all of physics study and graduate study amounts to understanding this formula and in which situations it works, in which situations it may break down, because it's not a finished subject. But I want to draw your attention to one very curious character that appears in this talk, and it's the imaginary number I. Okay, it's very strange that in the heart of physics, the number whose square is -1 appears in the middle of the formula. The way to understand this is that, when you go from real to complex numbers, this is a hugely powerful step in mathematics. Suddenly, every polynomial equation has the right number of roots. Everything fits together much neater. In the context of physics, the I signifies the following, that essentially all quantum mechanics is adding up phases. So every physical process is associated with a phase. This is the phase. And e to the I times a phase is a number whose square is 1. And that's essentially how the total probability being 1 is built into this formula. So I plays the role of ensuring that all probabilities calculated quantum mechanically add up to 1. So I emphasize this because actually this is the main reason why Stephen's initial approach to the beginning of the universe was not correct, in my view. He tried to adapt this formula to get rid of the I. And in this, he was following convention. It's called a wick rotation in quantum field theory. In various other areas of physics, you rotate time to imaginary values to turn this into a -1 and make this look like statistical physics. And so that mathematical step was actually unnecessary. Stephen thought it was essential. It was not, and unfortunately introduced some artifacts. So I won't talk a lot about the technicalities here. This is mostly going to be a talk about pictures, but I am talking about absolutely leading-edge research. Okay, so for that reason, many of the things I'm saying are not published. They will be published, but I'm more giving you my vision for where this field is going. Okay, so here's all-known physics. Within that formula are all the particles. These ones described by Dirac's equation, and these ones likewise. So the quarks make up atomic nuclei. The leptons, in particular the electron, makes up the electrons surrounding every atom. And then for some mysterious reason, there are 3 copies of three families of these elementary particles. We don't understand why yet, but they are replicated 3 times, and that will play an important role at the end of the lecture, where I'll tell you we may have understood what the dark matter is. Okay, the famous dark matter problem in cosmology. There are all these forces. I've mentioned them before. The weak forces are these, the nuclear weak force, the electromagnetism with its particle, the photon, and the strong force with the particle being the gluon. And here's the Higgs boson, which talks to everyone and tells them what their masses and charges are. So the one force tying everything together is, of course, gravity. And gravity determines the structure of space and time, the arena for physics, the arena within which all these particles travel around and interact. What do the observations say about the universe? I've told you the forces and the particles in the universe. What about the structure of the universe itself? And we are very, very fortunate to be living at a time when we've seen the whole thing for the first time. So in the last 20 years, observations have really grown vastly in their range and precision. And so we sit here in our solar system. As we look outwards, we're also looking back in time, because the light we received today was emitted at much earlier. It's taken time to reach us. And as we look outwards, we're seeing through the earlier and earlier universe. This is a time when galaxies didn't even exist, when the matter was slightly varying from place to place. There's something called a cosmic web, which is the progenitor of all these, of all the galaxies. As we get back earlier to the red shell, we're seeing the hot early universe, the surface of it. It's like living in a very hot spherical shell. We're in the middle of it. And this hot shell emits radiation, like any hot object does. And that radiation is the microwave background radiation, which travels through to us and traces all of these fluctuations that it goes through on the way. Beyond that surface of the hot Big Bang, if you go even further back, we can't do that using light, but we can do it using gravitational waves. Gravitational waves we can see all the way back to the Big Bang singularity itself, which is the edge of this picture. And there have been amazing advances. You may be following this, that gravitational waves were first detected a couple of years ago by the LIGO experiment, which simultaneously confirmed the existence of black holes and gravitational waves. And they were the two black holes which merged were emitting the waves in exactly the way predicted by general relativity. And then just last summer, last August, the LIGO experiment detected the merger of two neutron stars. They crashed into each other and formed heavy elements. And now we know the origin of most of the heavy elements in the universe, because gold and platinum and uranium were produced in such abundance by that event that there's more than enough to explain all of those elements in the universe. So we really learned a vast amount about how gravity and the particles and forces in nature interact. But I'm going to focus on the big picture in this lecture, the very big picture. And I think if you look at this amazing representation of the universe, the one thing that strikes you, at least it strikes me, is how incredibly simple it is. As we look out, the universe is not random and wild on large scales. On the contrary, it's extremely simple. And as I'll explain, I believe that the structure of the universe is actually, the large-scale structure of the universe is simpler than the structure of an atom. Okay, so the whole universe is actually the simplest thing in the universe. Okay? It's very paradoxical and very surprising, and I'm going to give you my best guess as to why it is that way. Okay. So here is what was seen. So if we look outwards to that red shell, this red shell, we can look outwards and measure the radiation coming off it, and that's what we see. That's the picture of the interior of that red shell spread out on a plane, like in an atlas. And these fluctuations are the seeds from which all the structure in the universe emerged. So here's the Planck Satellite launched a few years ago, which mapped this picture very beautifully. Now, when you look at that, your first response might be to say, oh, it looks pretty random. Okay, but it's extremely far from random. Okay, that picture maybe looks like it has no structure in real space, but you shouldn't look at things in real space. This is a system which has oscillations, and you should look at it in Fourier space, because Fourier space will capture those oscillations much more beautifully. So what we do is we Fourier transform this map to look at the normal modes of the radiation. And L here is the spherical harmonic number, L. Goes from the quadrupole up to about L of 2,500 in this map. The red curve is the theoretical prediction, which includes a few adjustable parameters I'll come to, but only a few. But you see the shape of the red curve matches the data exquisitely. And these theoretical curves were first worked out in the 1970s, a long time before the experiment was done, people anticipated this is what would be seen. Now, I was very fortunate to get into this game before, while not everything had been calculated. Okay. So me and my students in '94 decided to calculate the polarization of the sky. If you have light coming at you, it has an intensity. It also has a polarization, the difference between the intensities in two perpendicular polarization. So we worked that out, and we showed it was correlated with the temperature in a certain way. And so this is the theoretical curve we worked out. And so if you fit the parameters of the universe to this curve, you can predict this with 0 free parameters, okay? And you see it fits bang on. It's really amazing. So in a sense, this is the most boring possible result, okay? Because all the physics that was worked out, that is involved here, was really worked out in the 1920s and 30s by Einstein with his equations, and then Chandrasekhar, who studied the plasma physics and the propagation of light in the universe. So it was all we were doing. We were just turning the handle and working out what was predicted. At the time, all the experimentalists told me this will never be measured. Okay? It's way too small. You see, the numbers here are in microkelvin squared. So take the square root of that, and you'll get some number, something like 5 or 10 microkelvin. Okay? You've got to measure temperatures to that precision. At the time, the experimentalists said, no way, it's impossible, and the galaxy will be too noisy, and we'll never see this. And 10 years later, they were doing it routinely. So, so I've learned from that episode never to believe experimentalists. They're always much, much smarter than even they know. And if they just keep trying, they will find a way. So this is really an amazing episode in the history of science, that these curves were anticipated before they were measured, and they fit beautifully. And what is that telling us? Well, it's actually telling us something completely remarkable, that the universe is extremely simple. Understanding the universe is simpler than understanding even a molecule. Okay? It's really a very simple system. So I'm going to describe it in some numbers, and it's important to keep in mind what these numbers represent and which ones are important. So there's some numbers that sort of tell us about today. So how fast is the universe expanding? That's the Hubble rate, and it changes with time. The universe is actually speeding up its expansion due to dark energy, as we'll come to in a moment, but that changes. So there's nothing particularly significant about this number because it's going to change. Likewise, the age. Currently 13.8 billion years, but getting older all the time. So that's not a fundamental number, as far as we know. We don't live at a fundamental time. And the temperature of the universe. So as the universe expands, it cools. Why? Because every photon of light that's traveling through space is simply stretched by the expansion. Its wavelength grows with the size of the universe. That means its energy falls. So the temperature, which is determined by the frequency of the light, or related to it, proportional to each other, the temperature falls as the universe expands. So these are very important numbers to understand the universe, but they just represent as it currently is, and they're all changing. The fundamental numbers, from a theoretical point of view, are first these three numbers, the energy content of the universe. So given that there was a hot Big Bang, the early universe was full of radiation. Okay? And now as the universe expanded and cooled, various things were left over. The baryons, the ordinary particles that we're made of. Baryons are what atomic nuclei are made of. So the baryons were present in some small numbers. Signal from outer space. The baryons were present but you see the number of baryons per photon was a few in 10 billion. So basically the universe was full of photons, and then for every 10 billion photons you had a few baryons. And actually, if you go back to the very early universe, it was baryons and antibaryons in roughly the same number as photons, but with a tiny excess of baryons. And we'll come back to that. We now believe we can see why this happened, that there was slightly more matter than antimatter. And not in detail, but in broad brush, this is pretty much unavoidable. Dark matter, big mystery, that every galaxy is surrounded by a halo of dark stuff, which could just be some other kind of particle that happens not to interact with light. Its presence is very important because it helps the galaxies form due to its own gravity, and then it holds them in stable configurations. So the dark matter to baryon ratio tells you by mass what is the ratio of dark matter to the baryonic matter, the ordinary matter today, and it's about 5 to 1. And this is now measured to 2% accuracy. And then finally, the other ingredient in the universe is this dark energy, and I'll talk more about it later, but it's basically 70% of the energy in the universe. We say 70% of critical density. It's everything else, and this dark energy is very, very, very wonderful stuff. It's the simplest possible kind of matter, as I'll explain. So you have three numbers which tell you fundamental things about the universe. So if you take the photons as given, the light as given, you explain how many baryons there are, how much dark matter there is, how much vacuum energy there is, and that's it. For the composition of the universe, you need three numbers. Now, in addition to that, we have some structure in the universe. To describe the structure, we need to know the geometry of the universe. So the geometry wasn't perfectly smooth and uniform. These fluctuations, which gave rise to that web structure, were present in the early universe, and we can parameterize them as the standard deviation of the fractional energy density perturbation, delta, and that's a few parts in 100,000. Okay, so the universe was almost completely uniform across space, but it varied by a few parts in 100,000 on every scale. It turns out that this pattern of fluctuations was very nearly perfectly scale invariant. And that just means if I looked on a centimeter or I looked on 100 light years, I would see that the fractional deviation of the density in the universe is the same number to very good accuracy. So that's four numbers. Actually, I would say they're about 4.5 numbers you need. There was a famous book written by Martin Rees, who I think was a previous Peter Lindsay lecturer, called Just 6 Numbers. My response to his title is that cosmologists obviously can't count, because actually there are 5, and the way he counts is different than me. But he counts things as fundamental numbers, which are clearly not fundamental. But I'm also showing I can't count too. Now, why do I call it 0.5? This is because the final number you need to describe the universe is really small. Okay, so this number is the deviation from perfect scale invariance. So actually, if you look at these fluctuations, they're a little bit stronger on large scales than on small scales, but only a tiny bit. It's a deviation of about 1/30th in the exponent of the power spectrum, and this is really a very, very modest effect. So I call it 4.5 numbers to describe the universe, because if you got the 4 numbers correct, you'd be pretty happy, and this last one is really a small correction. And that's it. That's it. That's all the numbers we need to know to describe how the universe came out of the Big Bang. It's really pretty amazing, and as I said, the geometry of the universe is almost completely described by a single number. Just this level of fluctuations from perfect uniformity. So There are a few little details here. I've left out the masses of the neutrinos. These are something in the standard model. We know neutrinos have a mass. There's small corrections to these things. But there are many, many zeros in this description of cosmology. One of them describes the curvature of space. So in Einstein's theory, you can have a positively curved space or a negatively curved space, like a sphere or a hyperboloid. And that's allowed by his equations. But the universe doesn't seem to have any curvature. The dark energy could be perfect dark energy, and I'll explain that in a moment, or it could be some small deviant. It seems to be perfect dark energy so far. This index could change with scale. So far, we don't see any change. You could have non-Gaussian fluctuations, meaning that they couldn't be described by a normal distribution, right? Normal distribution in statistics is usually a very bad assumption. In the stock market or population genetics, the normal distribution is hopeless, or leads to big problems, because usually things are not normal. It happens, the universe has an almost perfectly normal distribution. In fact, so far there is no detection of deviation from normalness. And so these irreducible moments are zero so far. It's a good accuracy, better than a part in 1,000. So the universe came out of the Big Bang with these extremely simple fluctuations, normally distributed, scale invariant to high precision. And the final number, which seems to be zero so far, is how much gravitational waves came out of the Big Bang. Okay, so in Einstein's theory, space and time can get distorted, and those distortions travel as waves. So if the universe came out of the Big Bang in a distorted form, then as it expanded, those waves would travel through space. And so far, we don't see those waves, despite their having been predicted by the most popular theory, as I'll come to. This number seems to be zero. And this was a topic of a bet between myself and Stephen, which currently he is well on the way to losing. But unfortunately, I'm not going to collect. But I'll explain that in a little moment. So what I want to leave you with is that there are about 4.5 numbers you need to describe the entire universe. That's an amazing state of affairs. So the universe is astonishingly simple on large scales, but also very deeply puzzling. It really makes no sense. Okay? Why? Because the whole thing came out of a singularity. The whole universe, that big picture we see, all came out of a point. Right? Everything was on top of itself at a single point, at infinite density, almost 14 billion years ago in the past. So that absolutely makes no sense, but hopefully I will indicate why I think it will make sense very shortly. So the past is very puzzling. We came out of nowhere. And where are we going? We're going into this nothingness, the dark energy, which is this mysterious substance, currently 70% of everything. The dark energy is taking over the universe. And so ordinary matter like us is being diluted away. The galaxies, the stars, the radiation are being diluted away as the universe expands. The dark energy doesn't dilute at all, and so it comes to completely dominate everything, and as far as we can tell, it will be there forever. So we've got a very strange, bleak, empty future ahead of us, equally puzzling to the beginning. There's a few more puzzles. Why is there more matter than antimatter? Again, I'll point to this at the end. And what is the dark matter? I will point to that at the end. Here's dark energy. So at huge expense, we've done this survey of the dark energy in the universe. And so this is the multi-billion-dollar picture, which emerged. And as far as we can tell, the dark energy has absolutely no structure. Okay? What does that mean? So it is completely uniform in space and time. So if you move around in the universe, the dark energy doesn't change. if you sit at the same spot and wait, the density of the dark energy doesn't change. It's absolutely fixed for all space, for all time. It's immobile. In fact, you can't even move with respect to the dark energy. You know, if I run into this table, it'll be very uncomfortable. But if I run through the dark energy, it looks completely unchanged. And the reason is the dark energy is what we call Lorentz invariant. It doesn't matter how fast you're going, it looks exactly the same. So the dark energy is the simplest type of matter we know. It's invariant under everything we could possibly desire it to be invariant under. And so in a way, you could say it's not really surprising. Most of the universe is dark energy. This is the simplest stuff you can possibly have, right? It's totally featureless stuff. And it's 70% of all the energy in the universe. So most theorists have taken the point of view that the dark energy is a weird thing and an afterthought and an accident. I take the opposite point of view, that maybe it's the most fundamental thing, and that maybe the dark energy actually is what's in some way pulled the universe into existence. Because it has this very weird and wonderful property that it is gravitationally repulsive. So ordinary matter attracts under gravity, dark energy repels. It causes space to expand exponentially. So this dark energy has this wonderful property of making the universe grow. That was recognized way back in the 1930s. So let's look at gravity at the two extremes. First of all, let's think about the dark energy. It causes space to expand exponentially, and that has a very dramatic consequence. It means that if something is further than a certain distance from us today, then it will be carried away by the expansion of the universe faster than the speed of light. And then and that means, mathematically, that we will never, ever, ever see it, no matter how long we wait. Okay, so this dark energy has the bizarre consequence that it makes the observable universe finite. As long as the dark energy dominates, we will never see beyond a certain scale. And so the dark energy, in terms of what you can actually see, transforms the universe from being one that is in principle infinite to one that is finite. And that's a very big distinction. So this dark energy scale is about 10 to the 27 meters. And if the dark energy survives, we will never see anything beyond this scale. So I would say that's an extremely fundamental scale in physics. It limits us to scales smaller than that. On small scales, there's another scale also controlled by gravity, which is called the Planck scale. And the Planck scale is the following. Imagine I tried to make a microscope to see really small things. The smaller I want to see, the shorter a wavelength of light that I have to use. But as the wavelength gets shorter, the energy of the photons grows inversely with the wavelength. And so at a certain point, the energy of this photon in the rest frame of the rest frame of the photon and the particle it is seeing or scattering off, the rest frame energy is going to get so large that in this little region, you're going to form a black hole. And then nothing will come out of it. So you look at something under your microscope and you just turn it into a black hole. Okay, so that's the smallest scale it's possible to see. It's called the Planck scale, and it's 10 to the minus 35 meters. So gravity determines an ultraviolet cutoff in physics called the Planck scale, a short distance cutoff, and also a very large cutoff. So this is a very intriguing picture, which we've only learnt about in the last couple of decades. Now, where are we in this picture? Well, rather amazingly, we're bang in the middle. Okay? So if you take the geometric mean of the Planck scale and the dark energy scale, that's about the size of a living cell. And so the universe appears to be very simple on small scales, very simple on large scales, and really, really complicated on our scale. Okay? In fact, in a rather sort of grand picture, one could say that complexity in the universe is clearly growing very rapidly on our scale. I mean, even in our own society, we see complexity growing enormously as our technology grows. But the universe is a really very simple thing. By contrast, there's very little complexity on the Planck scale, very little on large scale. And so we live in the middle. We live at the leading edge of the universe in terms of complexity, and that's in the middle. And so rather than building the universe out of Lego, which I think has been the traditional model, you start with small things and you keep adding them up, and it gets more and more complicated the bigger you go. I think that's a wrong model. The way the universe seems to work is it's very simple on small, very simple on large, and actually it's the interplay between the small and the large which creates complexity like us. Okay, so let me now start with the conventional picture which tries to explain why the universe is so simple. Okay, and this is the picture which Stephen followed. He didn't invent. And he based his theory of the beginning of the universe on this picture. So what's the idea of the inflationary scenario? Now, I've already told you that dark energy is gravitationally repulsive. It's like dynamite. Put a little bit in, and it'll blow up the universe. So the whole idea of inflation is just to add a large amount of dark energy, much more than there is today. Put that in at the beginning of the universe, right? And that will make everything blow up into a big, smooth, flat structure, which looks like what we see around us. So that's the whole idea of inflation. And this is how it works in a little bit more detail. So you invent some new field, phi. It didn't appear in the known laws of physics. You've got to add it as an extra ingredient. It has some potential energy. That was Lagrange's potential. It's actually the dark energy density. And what you do is you want to put lots of this in at the beginning. So it's a large amount of repulsive dark energy to make the universe blow up. And then this field is going to roll down the hill just like a particle in a potential and oscillate around here. And while it is up the hill, it will cause the universe to blow up exponentially. When it falls down and settles at the bottom, that form of dark energy switches off, and the inflation is over. So that's the idea. It's a very simple toy model. It's literally like putting a spring in at the beginning of the universe. I want to get the universe bigger. What do? Well, put a spring in there. Does that sound right? I don't think so. But that's the idea. It really is like a compressed spring. Okay? So imagine you see a spring flying through the air at 5,000 meters altitude. You're going along in your airplane and you see this spring. What's the explanation? Well, one explanation is somebody compressed it, right? And it went boing and flew into the air. Does that really explain it? It's a chicken and the egg problem. Why was it compressed? I mean, after all, you go into a pinball parlor and you find a pinball flying through the machine. Well, of course, it could have come from the spring being compressed, but who compressed the spring? So the inflation theory is just like that. There's no explanation for why on earth there was so much energy stored in this inflaton field. You just put it in because you want the universe to blow up. Nevertheless, this became a popular idea. In fact, one of the few people to critique it was Roger Penrose, who's of course a figure of the same stature as Stephen and is still around. In fact, Roger was Stephen's PhD thesis examiner. And Stephen himself told me that Roger found an error in the thesis in the final chapter, as only Roger would. And Stephen had to revise his PhD thesis, which has now been published online. You can find Stephen's thesis. And the final chapter is rewritten with Roger's input. So Roger never accepted this inflation model. And his critique was the following, that basically is very, very unlikely. Okay? So if I walk into a pinball parlor, and what's the chance that that spring is fully compressed? Well, it's exactly, you know how to do this in statistical mechanics. You just work out the Boltzmann factor. You know, what's the chance that the spring stores? Probability is e to the minus energy over kT. And at any reasonable temperature, that will be a ridiculously small number. And so Roger made essentially this critique of inflation, that the chance of finding this field up the hill is ridiculously small. But he was ignored because there was a wonderful side effect. So it turns out that this spring, if you like, which was displaced, as this field rolls down the hill, like a particle on a hill, it would fluctuate due to quantum mechanics. Quantum mechanics causes things to be uncertain, causes the position to fluctuate, and the momentum. So it goes a little bit up the hill, a little bit down the hill, the wave function spreads, and you have fluctuations. So different parts of the universe would hit the bottom at different times and densities, and you would see the fluctuations we see. So there was a beautiful effect, which turned out that with the right type of potential, you could actually fit the fluctuations we see in the sky. And so for the last 30 years, people have spent their time building models like this, fitting them to the observations, and you can do it. It works. The only problem is there are thousands upon thousands of such models, and you can't, it's very hard to disprove the whole idea. It's an extremely flexible idea. The less wonderful effect is you get a multiverse. And so I'm sure all of you have heard about the multiverse and all the controversy about the multiverse. Is this science? Is it nonsense? The multiverse, essentially, part of the reason for it is this effect. So in some parts of space, this field would jump uphill, and you get even more repulsion and even more volume of space. It turns out those regions dominate. So most of the universe is still inflating. It's hard to switch off. It's like a genie out of the bottle. It's very dangerous and powerful stuff. And so the multiverse picture is like this, that there are patches of the universe where this field rolls down, but the vast volume of space is way up the hill, and it's expanding exponentially. So you get this crazy structure where each bubble is different, and we live in one part of the multiverse, but there are other patches which have different properties where possibly other people could be. So some people regard this as a great thing. I regard it as a disaster. I don't think any predictions are ever going to come out of this picture. And in fact, even you can probably see that even theoretically or mathematically, this actually can't be made sense of. There's no sensible probability you can assign to living somewhere in this infinite multiverse. So it's not a predictive idea at all. But from my point of view, probably what's wrong with it is that the picture of the universe is too classical. You see, you're putting in these quantum fluctuations, but you're not really treating the whole universe as quantum. And we know usually in quantum mechanics, or very, very often in quantum mechanics, one history dominates. Okay, so that's why we can think about the world as classical, because usually all the interference between the different quantum trajectories cancel out around one trajectory. There's a single dominant trajectory. Very rarely you can sort of stop that happening with symmetry. For example, in the double slit experiment, the particle could go through one slit or the other, and then you get interference. But in many, many situations, there's only one. And so my belief is that the way the universe works is there's really one dominant history. And the reason you're getting confused here is because you're trying to make a classical picture of something which is inherently quantum. There are many other reasons this picture isn't wonderful, it's very adjustable, you can tweak all of this and change everything. The other reason is that it's, not too long ago, it's been disproved, okay, in the following sense, observationally, okay, so don't even have to trust theorists like me. People realized that these fluctuations would give gravitational waves. And these cause a strain proportional to the potential. And so it turned out, so the experimentalists went chasing the signature, and then in 2014, they claimed they had seen it. Stephen announced on Radio 4 he'd won his bet with me. Okay, I had to go on the Today program and explain why I wasn't going to pay up. And what I said was, we know very well that when you do an experiment, if the result is surprising, you better repeat it. Okay? That's the first thing. And the second thing, you just have to read the abstract of the paper to see something was a bit fishy, because it said it disfavors dust at 2 sigma, but the claimed signal is nearly 6 sigma. So I called up the experimentalist and I said, how confident are you it's not dust? Is it 2 sigma or 6 sigma? And he said, well, just between you and me, it's 2 sigma. Well, I'm sorry, that's not a detection. And it turned out, in spite of all the fanfare, by the way, big prizes were awarded for this discovery to theorists. Okay? And, but it was fairly clear to quite a number of us this was a lot of wishful thinking. And sure enough, a couple of years, well, a year and a half later, the same collaboration was published an upper limit. Their claimed signal was at 0.2 for lots of gravitational waves. Upper limit is now 0.07. When that upper limit goes beyond 0.05, I win the bet with Stephen. Okay, so it's pretty close, and I think that will happen. So the good thing about this is that 10 experimentalist groups around the world are chasing this signal. The prospects are excellent for bringing this down to 0.01, maybe even 0.001 is possible, and we should see that in the next 10 or 15 years. So this exclusion of gravitational waves is coming. Okay, now I've got to speed up. I'm going to jump a little bit. So I want to talk about Stephen's proposal for the beginning. I've alluded to this a little bit. Here's the inflating universe, this exponentially growing universe. Stephen said what makes sense for a beginning is that we sum over 4 geometry. What is a 4 geometry? Well, it's space. You should think about space going around this picture, time going along it. And so this, obviously this is a 2-dimensional geometry that I've drawn, but it's representing a 4 geometry, in which this, for example, would be a 3-dimensional sphere, and that would be time. So Stephen pictured all of space and time coming out of an initial geometry of 0 size, or a point. And he was able to do this by making time go imaginary, which I've already talked about earlier, at the very early moments of the universe. It's a very, very beautiful idea. It's an idea according to which the laws of physics determine their own initial conditions. Okay, it's quite different than classical physics, and a very, very profound and beautiful idea. Only one problem, it's wrong. Okay? And so I'm not going to, I think in view of time, I'll describe in detail if anyone wants the details. But basically, they made an original claim that out of this proposal, called the no-boundary proposal, it means there was no initial boundary of the universe. Out of this proposal, they claimed you would get Gaussian or normally distributed fluctuations of just the type we see. Unfortunately, when we recalculated this using a technique which was not available at the time in the 80s. It has a fancy name, but this I'm not going to describe the mathematics, but essentially it's doing this summation over phases, the e to the I phi, properly, taking into account all the interference in the phases. And for those of you who do mathematics, this is the saddle point method or stationary phase method. And there's something called Picard-Lefschetz theory, which is the high-dimensional version of that method. Very beautiful mathematics, which wasn't used until our work in physics. And when we did this, we found that actually they had a minus sign wrong in the exponent, and the perturbations are out of control. So the end, but not quite, because it turns out, I believe, that Stephen's intuition was correct, even though the technicalities were not. And let me explain this very briefly. I'll try and just take 5 minutes. So is there any other situation in physics where we see something created? You know, we have to describe how the whole universe was created. Do we see anything like that anywhere else in nature? And it turns out you don't really have to look very far, because particles are created out of the vacuum. How do you make particles out of the vacuum? Well, you turn on an electric field. You see, if you turn on a very strong electric field, it pulls electrons one way. They're pulled against the field because they have negative charge. The horizontal is time, vertical is space. So the electron is pulled one way. The anti-electron is pulled the other way. So matter and antimatter exist in the world. You switch on a strong electric field, you will literally pull a particle-antiparticle pair out of the vacuum. Right? So, in fact, this has never been done experimentally. It's just at the threshold of what's technically possible nowadays. It probably will be done in 10 or 20 years. But we're extremely confident that this would happen because basically we see it happening in collisions of the type that happen at Large Hadron Collider and other particle physics experiments. So we can't actually turn on an electric field of this strength in a big volume of space, but we can just collide two big nuclei, for example, and then you see this happening all the time. So in this case, you see, we are external observers. Whoops. And we're seeing, what we just see is electron-positron pair produced, right, in space-time. Now, there's an alternate picture of this, which is the following, which is that actually the positron, what is a positron? It's an antiparticle, antimatter. What is it? It's just matter going backwards in time. That's all it is, okay? So that sounds very weird. What? Things can go backwards in time? The answer is yes. In quantum field theory, things are allowed to go backwards in time. And this actually was the picture which Richard Feynman favored for how to describe particle collisions. You can use it to describe all the phenomena involving matter and antimatter. Just think of the antimatter as going backwards in time. So this is the picture, the positron. What is a positron? It's actually an electron going backwards in time. So here's this backward-going electron. Time is going this way. My time is going this way, right? Our time, the observer's time. But the particle has its own clock. It doesn't have to agree with our time at all. Okay, so the particle's clock is going forwards in time all the way along here through this trajectory. In this region and this region, it's a classical particle. In this region, it's very quantum. Okay, so I think I'll skip this unless anybody asks me. It turns out the particle and antiparticle are related by a symmetry called CPT. Charge conjugation, parity, and time reversal, very fundamental symmetry in physics. Here, I'll skip this unless somebody asks me. They're cute movies showing you exactly how this process happens. I'm going to skip this too. So I'll answer any technical questions afterwards, but this is the picture that emerges. Just like you had here's a universe, here's the anti-universe. This is the analog of the electron. This is the analog of the positron. But you can think of this as if this region of the universe is really the same as this region, but going backwards in time. Backwards in time means becoming smaller, contracting. That's before the Big Bang. Then there's some very quantum region, just like there was with the pair creation, and then it comes out as a universe. But a better way to think of it is that actually the universe we live in came out of this fuzzy quantum region. Say we live on the electron, right? We don't really care about the positron. I mean, we're a one-dimensional thing, and all we're aware of is the electron. Okay? So here's the universe. It would be completely equivalent to describe that as an anti-universe. And because physics is CPT invariant, there's a very fundamental reason for that. The laws of physics are completely invariant under CPT. Whether you describe us as the universe or the anti-universe makes no difference. These two are completely equivalent descriptions. And so we were very excited when we realized this possibility. And we called it, I have a Dutch PhD student who knew a little bit about Dutch intellectual and philosophical history. And he told me, oh, this is just the causa sui universe. Causa sui means it caused itself. Okay, and this is the idea of Spinoza. He was interested in causality. You know, what caused what? And he coined this phrase, causa sui, causes itself. By causa sui, I understand that whose essence involves existence, or that whose nature cannot be conceived unless existing. And so it caused itself. So we answer the question by basically reframing it in such a way that it's meaningless. Okay? And so what caused our universe? Well, it was our universe that caused our universe in this picture. So I hope you feel totally satisfied with that. Again, I had a little bit about the dark matter. I will just tell you this in words. I've already mentioned the neutrinos, right? We have these strange particles in nature called neutrinos. They have no electric charge. The neutrinos we see are almost perfectly left-handed. Okay, so if their momentum is along the thumb and you try to get the spin, it will be along your fingers. So all the neutrinos we see are left-handed. There are no right-handed neutrinos. However, we know these neutrinos have tiny masses. Those are observed. And those masses indicate that there are right-handed neutrinos as well, which are much heavier than the left-handed ones. So before our work, no one knew how to... The right-handed neutrinos, by the way, are heavy and have no charge, don't interact with light. They're ideal dark matter candidates. They're just the perfect dark matter candidate. But before our work, no one knew how to calculate their abundance. You have this particle, it must be there, very heavy, it doesn't couple to light. But in the conventional picture, you couldn't calculate its abundance. So what did people do? They assumed it's unstable, and so it'll go away. So the embarrassment will be avoided. This is literally what happened. It won't be embarrassing because it'll just disappear, and so who cares? Well, in this framework, we could calculate the abundance. Okay, so once you have that, you can say, well, maybe it's stable. Maybe one of those three right-handed neutrinos are actually stable. And that, I claim, is the simplest candidate for dark matter, because basically we know these particles have to exist for other reasons. It's not a big assumption to, it's not difficult to build a theory so one of them is stable. And if you do that, it's the dark matter. So now you have a really, really precise and definite theory of the dark matter. It's just one right-handed neutrino. We know how to calculate its abundance. We can tell you what its mass is. It's exactly this. And there are various other predictions that follow for the neutrinos we see. Well, 5 days after our paper, this was earlier this year, And I think the 5 days after actually happened on April the 1st. Okay. But so this paper actually appeared, I believe, on April the 1st. But it wasn't a hoax, as far as I know. And the revised version is not on April the 1st. There's a new, longer version. And you'll notice they say here the dark matter particle is this right-handed neutrino, and this confirms the CPT symmetric universe. So really amazing. Okay, so what happened is there's a beautiful experiment at the South Pole, balloon experiment looking for cosmic ray showers. And over the last couple of years, and we were not aware of this when we wrote our paper, they saw 2 showers going upwards from the Earth, not coming in from outer space, but coming out of the Earth's interior. 2 of them with a huge energy, right? This is 4.8 billion times the mass of the proton. It's a very heavy particle. So they saw it at just the right energy, and we're now busily exploring if this really makes sense. But it may be that we've cracked the dark matter problem, and in a very surprising way. I'm not going to talk about the flatness of the universe. There are various other predictions I won't talk about unless anybody asks. But watch this space. I think it's very exciting. In my view, cosmology has a chance of solving all these big puzzles without adding more and more and more arbitrary ingredients, rather just understanding better what we already know. So thank you very much.
It's now my pleasure to invite Professor Alan Heavens to propose the vote of thanks.
Well, it's a great pleasure to give the vote of thanks after such a wonderful talk. Also because I've known Neil for a very long time, since the late 70s when we were both undergraduates at Churchill College in Cambridge doing the same course. And I got to know him best during a notorious long vacation course where we would do theoretical physics for 4 weeks. And Neil and I would work together on tutorial problems. They were quite hard. If there was a particularly difficult one, a fiendishly difficult one, we would think about it hard, and then Neil would tell me the answer. After that, he embarked on a glittering career that's been notable for many awards and prizes. And I'm sure that one that he's particularly proud of is the TED Award for setting up the AIMS African Institute for Mathematical Sciences, which, as you heard, started in South Africa, but now spreads to a number of other African countries. And Neil, I'm sure you'll be interested to know that one of my own postgraduate students who comes from Mauritius, and he's here in the audience today, did a master's degree where he studied 3 days a week at AIMS.
Oh, wow.
And now won one of the Imperial President's scholarships to pursue a PhD in cosmology here, following in your footsteps.
Fantastic.
Neil has given us a wonderful talk covering one of the most intriguing issues in science, the nature of the quantum universe. And I think it certainly comes into the category of fiendishly difficult questions. So I can think of no one better to tell us what the answer is than Neil. So please join me in thanking him for a wonderful talk.
That brings the evening's proceedings to a close. Thank you for coming.